So we have discussed Raoult's law, okay, and the application of the Raoult's law in determination of the mole fraction of the two mixtures and the determination of the vapor pressure. Okay. Now, let's say if you have a non-volatile solute, okay, okay, in a solution, you have a solute and you have solvent. Hmm? Okay, let's say your solute is non-volatile, is non-volatile. Last video what we have seen is the mixture of two volatile substances. Okay. Now, in between them, let's say one of the component which is a solute is a non-volatile. Okay. So then what Raoult's law says? Raoult's law says that for any solution, the partial vapor pressure of any each volatile component is directly proportional to the mole fraction. I'm repeating again. Raoult's law said for any solution, the partial pressure of the volatile substance is directly proportional to the mole fraction. Okay. Now let's say this is also binary solution. If I have okay. So for the solvent, so the volatility will be come from the solvent here. So in case of the solvent, we can write P1 is equal to P10 into X1, right? This can we can write. Now, since solute is a non-volatile, so the extreme pressure, okay, the total pressure, which is the P total, P total will be equal to small p1 because the total vapor pressure is will be come from the your vapor pressure exerted by the solvent, so which is nothing but the p10 into x1. Hmm. Okay. Now if we plot, okay, what we will get? If we plot the speed total with respect to x1, if we plot, okay. So x1 is here it is 0, it is 1. Same. If I put x1 is 0, then p total will be 0. 0. So this point, this point, p total will be 0. And if I say x1 is equal to 1, then your p10 will be equal to the p total here. So this is the line. Hmm. So this is what? This is basically the vapor pressure of pure substance. Clear? Hmm? Clear? Okay. So this is the plot. Say if someone asks you in question that what will be the plot in case of if one component is non-volatile, okay, then we will just straightforward go through this. Okay. Okay. So this is if in a solution, if one component obeys Raoult's law for all the concentrations, okay, if all the concentration, if this solvent component is following the Raoult's law, hmm, following the Raoult's law, then the vapor pressure will vary linearly from 0 to the pure pressure, vapor pressure of the pure solvent. Hmm? Okay, so Raoult's law. So those solutions, okay, those solutions which follows the Raoult's law, okay. So those I would say solutions they follow Raoult's law, Raoult's law for all concentrations, for all the concentration range, this X1 variation, all the concentration range, those solutions are called ideal solutions. Ideal solution. and who they does not follow, they are known as non-ideal solution. Non-ideal solution. Hmm? Okay. Now, what is the characteristics of an ideal solution? Just what I said. It follows Raoult's law throughout the any composition. Okay. Now, properties. If I write down the properties, now since it follows the Raoult's law throughout the composition, that means the exchange of the heat, the I would say the mixing of the two components, that the heat generated, the change in heat when two components are mixed, that will be zero, because it's ideality condition. Delta H mix will be equal to zero. Okay, and delta V mix will be equal to also zero. Now why this is? Think, think why. Okay, why? Hmm. Okay. And another beautiful thing about this ideal solution is what? Here you have what? You have a solute. Okay, sorry. You have solute. Okay, right? You have a solvent. Alright. Let's say you have a solid molecule AA, solute. Okay, and solvent molecule, let's say BB. It's a molecule. So what will be the solution? AB. Okay. Now, in ideal cases, ideal solutions, the solute-solute intermolecular attraction force will be nearly equal to the solution intermolecular attraction force. That means your in case of ideal solution, E of AA, E of BB, E of AB. Okay, I would say intermolecular means potential energy. Potential energy. Okay. Now let's say in, so what is the example? Example. Okay, I will discuss this later. Later. So what is the example? Benzene plus toluene. Benzene plus toluene. N-hexane plus N-heptane. Okay. So these are the solutions of an ideal solution. So what is the definition of the ideal solution? The ideal solution is such a solution is an ideal solution is such a solution where the delta H mix and delta V mix is equal to zero. Hmm? Number two, the solute molecules, the input in intermolecular attraction force of the solid molecules is nearly equal to the solid molecules and the solvent molecules is nearly equal to the intermolecular attraction force of the solvent molecules. Okay, and what are the examples? The benzene and toluene mixture and mixture in hexane and inheptane. Okay, now ideal case means they does not mean, now obviously if you have a mixture they exist, but most of the cases what we follow is that linearly throughout the concentration, no solutions, no solutions linearly follows Raoult's law. Hmm. Okay, let's look into that. Those solutions are known as non-ideal solutions. Okay, if I look this way, okay, non-ideal solution, non-ideal solutions. Okay, now non-ideal solutions. See, let's say if you have a standard value, some you are, let's say someone gave you, your instructor gave you that you should run through a line, hmm, a line along the along through the line. Okay, okay. Now, let's say wind is there somehow. That means if you run through the line, that means basically you are doing some ideal case. Hmm. Okay, ideal case, and you are ignoring the if wind is not there, any high wind is not flowing from this side or this side. What you will do? You will run through the line on the line. Okay, then that will be the ideal case. But let's say if this way the wind is coming, then there will be a deviation, your deviation from the line, and then you run. Okay, and from here also, if wind comes from this side, so there will be a deviation from this line, and then you can move on. Okay, so that means there can be two types of deviation in case of non-ideal system. Let's look into that. Okay, number one, if I talk about, let's say, so this and next is in one important concept is that where this deviation comes from. Hmm. Okay, first of all, let me tell you for non-ideal solution. So ideal solution, as I said, the enthalpy of mixture is equal to zero. Why? Because the attraction force between the solute and the solute solvents are same. So that's why if you mixed two solutes, solvent and make the solution, the overall free energy or overall enthalpy change in the solution becomes zero. But in this particular non-ideal case solution, the delta H mix will be greater than zero. Hmm? And delta V mix will be always greater than zero. This is the condition. Hmm? Okay. So what happens? So as I said, there will be a two types of things. Okay, two types of behavior will be observed. Okay, first case. First case, let's say you have what I said here. Okay, your solute. Okay, let me write it here. Solute is my AA, solvent is BB, SOLUT, and solution is AB. Okay. Now let's say if I put such a condition where your solvent solute force is weaker than solute solute and solvent solvent force. Okay, means solution solution force or energy, intermolecular attraction or energy, whatever, is weaker compared to EAA or EBB. If I say this condition, so what will happen? Look, I will directly draw the graph and explain. Okay. So what was the graph? You have one component is here, another component is here. Let's say this is PA0 and this is my PB0. Okay, so this will be there, this will be there, and this will be there, and this is my XP, the mole fraction of component B. Okay, so this was my original graph from the Raoult's law. So what happens in this case? See, hmm, your solution has lower, weaker. That means the more solutes and solvents, they will much more be their own, right? Now, if they are trying to be their own, what will happen? The evaporation of the individual part, that is solute and the solvent, will be high because they are not together. They are not coming together. So they will behave independently. And due to this independent behavior, they will be prone to prone to more vapor, prone to be in the more vapor state. Am I clear? Let me tell you another. Again, E solution, that means solution AB interactions is weaker. Okay, compared to AA and BB. That means the solutes and the solvents, both volatile components, will have their own identity. They will try to be their own, right? So what will happen? So they will be more prone towards the vapor phase. And in that case, what will happen? The pressure, vapor pressure will increase. So what you will see here, this is the normal line, that is the state that what your instructor was told you to go. But since the vapor pressure is higher, because the each solute and solvent, they have their individual identity, so what will have? They will have a positive deviation from the vapor state. Positive deviation from the vapor, your Raoult's law. So this is basically, this will be now the vapor pressure of the solution, solution in the vapor phase. Okay, and in this case what is happening? It is a positive deviation from Raoult's law. Hmm? Okay, so it will be a positive deviation from the Raoult's law. So in another case, so just I will take the opposite of this case. So E of solution, that is AB, is greater than E of AA or E of PB. This case happens. What happens in this case? In this case, again, if I draw the graph, okay, so this point and this point, hmm, so this is my PA0, this is my PB0, this is my XB10, okay, so this is the graph and this is the graph, okay. So now what will happen in this case? The solution, the solvent and solute, they are strongly having a strong interaction. Okay, that means there the individual identity of the solute and the solvent, the individual behavior will be less. Okay, and in that case, the number of molecules in the vapor phase of the solutes and the solvent will be also less. So the vapor pressure will be also less. So in this case, what will happen? There will be a negative deviation from the Raoult's law. That means you are diverted again from the line. So this is basically a negative deviation from our law. Clear? Okay. So this happens in case of the non-ideal solution, and this happens in the real life. Hmm? Okay. So let me give you an example of this case. This case, the example is your ethanol in ethanol and acetone. Example number one, ethanol plus your acetone. Okay, and example number two is your carbon disulfide CS2 plus a mixture of CS2 and acetone. Carbon disulfide and acetone. Okay, and what happens in this case? The example is number one is your phenol and aniline, phenol and aniline, and number two is chloroform and acetone, chloroform CH3 and acetone. Okay, so these are the examples. So the concept you need to learn is that the negative deviation and the positive deviation from the Raoult's law plot, and why this originate the positive deviation originates when the solution solute solvent interaction is lesser compared to the solute solute and solvent solvent interactions, and negative deviation originates where the solute solvent interaction is higher compared to the solute solute and solvent solvent interactions. Okay, So this is the concept of the non-ideal solution. So now, when I say this non-ideal solution, this ideal solution and the non-ideal solution, the both cases they are at a particular constant temperature. Okay. Now, what happens if I vary the temperature? Hmm. Because each of all the following, all the substances, I'm rubbing it out, all the substances has a particular temperature, like melting point. They have a particular boiling point. Okay, all the substances. Now, if I think in this way, okay, like all the liquid and or the vapor substances have a vapor pressure, and liquid substances they will vaporize and they will show the vapor pressure. Now, what happens that if we think that if a element, if a substance melts, okay, at a particular temperature, that temperature is known as the melting point of the substance. But if I make in this way that the substances, if I mix both of substance, let's say I have substance A, substance A, and I have substance B. This substance B has melting point Ta, and this has melting point Tb. That means if just compare with Raoult's law, just what I said. Raoult's law, what you have in pure form, you have a pure vapor pressure of solute and pure vapor pressure of solvent. So this is also pure melting point. At melting point, obviously at constant pressure happens. Okay, you have temperature melting point Ta and Tb. This is in the pure form. Now, if I mix both of them, if I mix, then what will be the melting point? What will be the melting point? Let's say T mix. Okay. Now this T mix will be greater than Ta or Tb, or this T mix will be lesser than Ta or Tb. Now those mixtures, okay, those mixtures having the same composition, okay, those mixtures of, let's say in the mixtures of A and B, okay, mixtures, and now when this condition I will use, okay, let's say I'm taking the mixture of A and B. Now I found it out somehow that when I'm mixing these two substances, so this component A plus component B, and in case of this vapor, we have component A and component B. This is vapor phase and this is liquid phase. This you have, right? Vapor phase and the liquid phase. So here it was y1 plus y2, and here it is x1 plus x2. This is the case. X1 plus x2, more fractions. Now, if you have that they have a same composition, that means x1 with y1 and x2 with y2. If you have their same composition in the liquid and vapor phase, and they will boil, they boils or melts, whatever boils. Okay, sorry. Your boiling point. Okay, because we are dealing with liquid. I'm very sorry. Okay, boiling point. Dealing. You can do melting point also. Boils at same temperature. Same temperature. That means what I'm trying to say. They both of them have same composition. Same composition. That means x1 is equal to y1 and x2 is equal to y2. X2 is equal to Y2 in vapor phase and liquid phase, and they boil at same temperature. Okay, same temperature, then that mixture is known as azeotropic mixture. Okay, azeotropic mixture. It's a new type of mixture you can think of. Okay, it It has a huge range of application in industry, obviously, because the azeotropic mixtures are particularly those. Okay, let's say if you have a huge variation of this PNTB. Okay, now you mix them. Okay, and after mixing, you will find a new melting point. In that melting point, you can melt both of the substances or boiling point. Oh, sorry, boiling point. You can boil at particular at a temperature both of the substances together. Okay, and from so basically it's a I would say same boiling point mixture. Is that as if someone asks you in one word then what do you how do you define azeotropic mixture? Then we would say the azeotropic mixture is a same boiling point mixture. Okay. Now this azeotropic mixture will have a two cases as I discussed here. This is in one case and this will be another case. Okay, let's look into that. So case number one, if I look at it. Okay. So in this case, if I draw the plot first, if I draw, okay, okay. So what will happen? The solution will show large positive deviation from the Raoult's law from minimum boiling azeotropic mixture as a composition. Okay, let me rephrase you this way. Okay, so let's say if you have this is a mole fraction, let's say composition. Let's say I'm talking about X2. If I talk about okay. Now when X2 is 0 and this is X2 is 1. Now when X2 is 0, so this is my T1, sorry, TA, XB will be better, right? TA, okay. And let's say TB, and I'm considering this is the place, okay. TB is greater than TA. So this is my TB. It is exactly the same like your Raoult's law. Just here there is the variation of the temperature. Okay. Acha. Now let's say you are what you are doing, you are basically varying the concentration of XB and XA. Okay. Somehow you found it out that if I vary the concentration, okay, if I vary the concentration, okay, so what will happen? So this will be the case. This will be the case. Okay. This will be the case. Okay. That is the concentration. Now you see here very clearly there is an intersection point. There is an intersection point, right? There is a intersection point. Okay. So in this case, what will happen? Now in this intersection, now as I said that Raoult's law, since Raoult's law is there, it can show positive deviation, it can show negative deviation also. So this graph and this graph. I will rub out this. Okay. So at this point, their intersection there. So this is this point. Okay, this point will have a particular temperature. Let's say T mix. This is a particular temperature T mix. Okay, and this point is known as your azeotropic composition. Azeotropic composition. Okay. Okay. By the way, here your XA is not equal to XB. This is not the condition. Okay. So they will have a particular ratio, okay, concentration ratio such that they will have a fixed boiling mixture. Fixed boiling point. Okay. So this is see very beautiful because if you mix them, okay, if they have a huge difference of the boiling point, okay, if you mix them, they boils at a particular same temperature, and that temperature is based on a particular composition. Okay, and if you find out this composition, which people does in industry, in science labs, everywhere. Okay, so this composition, if you found it out, you can find that particular mixture temperature also. Hmm. Okay. Now this is another thing is I want to mention here is that the this if this temperature is lesser than this temperature mixture temperature is lesser than both TA and TB. So this is known as your minimum boiling azeotrope. Minimum boiling minimum boiling azeotrope. Okay. Acha. Now another thing here I want to mention is that okay. So another case happens. Hmm? Another case, if I write it down, okay, same way, same way, okay. So this is my TA and this is my TB, okay. So this is my XB, hmm, okay. So there may be some cases that since the temperature, right, okay, temperature, right. So there may be some cases where if you have the mixture, the temperature of the mixture can be greater than both of the cases, right? So what can happen here, right? This will happen. So this will be my that azeotropic composition. This is azeotropic composition. Hmm? Okay, and this particular temperature will be my T-mix. Okay, so in this case, what is the what is the name of this case? This is the maximum maximum boiling azeotrope. This is a maximum boiling azeotrope. Okay, so let me give you examples of this part. Hmm, example. Okay, let me write here the example. Okay, write here the examples. Hmm, okay. So example of this minimum boiling azeotrope is basically let me give you the example. Ethanol uh, it's ethanol water mixture. It's ethanol water mixture of 95% ethanol. Ethanol water mixture of 95% ethanol. And in case of maximum boiling mixture is nitric acid and water is nitric acid and water. Okay, it's 68% nitric acid. Okay, 68% nitric acid. Okay, so what we have learned so far. Okay, we have learned many things first of all. Okay, what so we have learned is Raoult's law. Okay, vapor pressure. More the escaping tendency, there will be more vapor pressure. Number one. Number two, the application of the vapor pressure Raoult's law. Ideal solutions, non-ideal solutions, the behavior of the ideal solution, non-ideal solutions, examples. Non-ideal solutions which shows one positive deviation from the Raoult's law and another shows the negative deviations from the Raoult's law. Okay. Then if I instead of pressure, if I take the temperature of boiling point of the two substances, solute and solvent, then what will happen? In that case, if your mixture in the mixture, if your vapor phase concentration and the liquid phase concentration is same, so they if they attain at a particular temperature, they have a same your boils at same temperature, then those mixtures are known as azeotropic mixture. And the azeotropic mixture, we have two cases. Now, if one case your mixture temperature is lesser than compared to the both of the substances, boiling point substances, then it is known as the minimum boiling azeotrope. And if it has a higher mixture temperature compared to the other two substances, and so it will have a maximum boiling azeotrope. Okay, so till now this is fine. So this now I am finishing your lecture number 5. Hmm? Okay, and next, I will next from next onwards, I will talk about the solubilities, the Henry's law, and then directly I will move to the your colligated properties. Okay. So till now you just read your NCERT books, okay, and whatever books notion you have, and try to figure out few exercises and few numerical problems that I would love to discuss in the next video lecture. And okay, and just go through the theories, whatever you have in the book, and just try to solve the numericals. Okay, thank you.